मुझे करनी है मीटिंग तो
Okay, so hopefully all of you can hear me. Anyway, yes, I suppose you have to mute your, I have to mute yours, all of you. Anyway, welcome to MA222. And I know that it's a difficult time for everyone. And so, okay. So we are going to start, maybe a few words how we are going to go about this course. And of course, we also have to evolve as teachers or instructors because we are also not too familiar with online teaching. So hopefully we'll improve with time. So you may have to bear with us or bear with me, particularly in the initial part when I need to figure out what would be the best way to proceed. So, but yeah, first of all, hopefully you'll be taking good care of yourselves wherever you are. And we hope that maybe the situation will improve and at least towards the end of this semester or certainly the next semester will be in campus. Okay, so what I'll be doing, I'll be making some slides and I will explain those slides. So let's just first look at the syllabus or the contents. And let's see. Okay. But yeah, it's so let me. So can you see the syllabus? Maybe one of you, maybe Shamik can answer.
Yeah, it's visible, sir.
It's visible. Okay, fine.
Yeah, okay. Now it's reference coming.
Okay, fine. Yeah. Okay, so as you know, you must have seen the syllabus. This has two components. The first one is elementary number theory, and the second component is algebra.
Yeah, you can make it full screen.
Okay, I'll make it full screen. Is it better?
Yeah, fine.
Okay. Yeah, so this is the syllabus, and yeah, probably it's correct that we should start with elementary number theory because you all know that mathematics starts with numbers, although it may not necessarily end with numbers, but certainly mathematics started with numbers. So, and we'll go to the very basic principles of numbers or the number theory. It's one of the oldest branches of mathematics. And our starting point will be well-ordering principle. So in number theory, elementary number theory, we mostly concern ourselves with natural numbers, which is 1, 2, 3, 4, etc. And the set of integers, where like you include 0 as well as -1, -2, etc. Okay, so basically most of the time we'll be concerning ourselves with integers. And in fact, that will be our basic example of a group as well as a ring, because in the algebra part, that is the most, because in some sense, you can say that the group theory, it's like a generalization of integers under addition. Okay, because integers have addition. They have an identity element. It is closed under addition. If you add two integers, you get an integer. There's an identity element like 0. So if you add 0, you get back the same number. So there's an identity. And there's an inverse, because for every integer, you have its additive inverse. When you add them, you get 0. Okay. And of course, the associativity property is there, that whether you a plus b bracket, bracket a plus b plus c is same as a plus bracket b plus c. So that associativity is essential. So when you have this kind of properties for a set with some operation, binary operation. Binary meaning you are adding two integers, so it's like a binary operation. So that's the example of a group. And if we consider the other operation also, because integers, I mean, that's why also, by the way, that's why we cannot stick to just natural numbers, because we will not be having additive identity and we will not be having additive inverse. So that is one motivation why we need to go for integers. Okay. Okay, so that is integers under addition, but also integers and multiplication, because I can multiply two integers and get another integer. This operation is also associative, and this also has an identity in the case of integers. That is 1. Like multiply by 1, you get back the same integer. But this time you do not get an inverse, multiplicative inverse. So there is some limitation to the multiplication structure. And then since you have two operations, additions and multiplications, it is natural to ask whether these two operations are compatible or they commute, in the sense that if you add first and multiply, or whether you multiply first and add, whether they are same. In other words, whether a times bracket b plus c is a times b plus a times c. So on one side you are doing the multiplication first, and the other side you are doing the addition first. This is like a distributive law. So these integers have these two operations. When we consider both the operations, that is basically a ring structure. So again, integers under addition and multiplication is a good example, or this is something that we try to generalize, which is known as a ring structure. But of course, we like relax some of the requirements, like because multiplication in integers is commutative, like 5 into 7 and 7 into 5, they're the same thing. But in general ring, we don't want to insist on that, so that we can look at more objects. There will be more objects satisfying our requirement, and we can study the structure. So we'll see that later. The integers is actually, this is a very special type of ring. Yeah, so but before going into groups and rings, this is the motivation for us to consider the number theory part first. And in fact, we'll be requiring these basic properties to prove other properties for groups. Okay, so we'll actually frequently need those properties anyway, even if we don't consider them as groups or rings to start with, but we will need the properties of integers to prove many properties for groups and rings. So that is another motivation why we need to do this number theory. Earlier, this number theory part was hidden, like we used to start with groups itself, and when as and when required, we used to call back the properties of integers that we would be using. But now it is probably better that number theory gets its due respect and proper place, and as a good starting point. And also it has an advantage because it is something we are all familiar with. Okay, if we straight away, if we start with groups, maybe that may seem a bit abstract, but see, these are very concrete objects. Integers under addition and multiplication, probably the most familiar object in mathematics to all of us. In some sense, it is more, I would say, it's more familiar, much more familiar than the vector space structure that you did in your MA101, or even your real analysis like convergent sequences, etc., or is Riemann integral. It is, in some sense, it is even more basic. So, okay, so let me go over the contents that what we will be doing. The first one is well ordering principle. Okay, and that is a statement that will take it for granted. And with that,
Sir, are you there?
Hello. Hello.
Hello.
I've been talking, it is not all the while I was muted.
Hello.
Just a moment.
Yeah, it's fine now.
See, no, but all the while you were not listening. Was I audible?
So we
Yeah,
heard
yeah.
you till you were going over the contents. After that, you were unaudible.
Okay, so anyway, just please let me know whenever I'm inaudible or you are not following, just let me know but I was audible till I went to the syllabus, right?
Yes, sir.
So did you hear about what I was saying about well ordering principle?
No,
Till
no.
that part we heard.
Well ordering principle you have heard, right? Okay.
Yes.
Okay. So again, let me see. That's a problem. Sometimes it may crop
The
up
slide
again.
were not visible that time.
Now it is fine. Maybe it is an internet issue only. But is it clear now? Is it visible?
Yes, sir, visible.
Yeah,
Okay.
it is now visible.
Okay, fine. Okay, let me continue again. So after well ordering principle, we go to division algorithm. And we know what division algorithm is. Like you can divide a by a positive integer and you get a remainder which is non-negative and less than the divisor. Again, this property will prove using well ordering principle. And then we'll look at GCD and LCM, the greatest common divisor and the least common multiple. And Euclidean algorithm, which is very useful, which tells us how we can find a GCD without factorization, because factorization is a much harder problem. Finding the GCD is far easier. We'll see that using basically division algorithm, we can find GCD without factorization. Okay, as you know, I mean factorization. If it were easy, then many of these RSA crypto systems will crash because that is based on the hardness of the factorization problem. Okay, so that's Euclidean algorithm. And once we have all this, we can also solve linear Diophantine equations, like basically ax plus by equal to c, where a, b, c are integers, and we look for solutions in integers. Okay, so basically, essentially, everything will boil down to division algorithm. So this part we do. Then, of course, the building blocks, because the integers, this fundamental theorem of arithmetic, that means every integer is a product of finitely many primes. So that means to understand integers, the key is the prime numbers. So we'll discuss properties of prime numbers, like like there are infinitely many primes, etc. There are many other properties or many other open questions which are still unresolved, like this twin prime conjecture, Goldberg conjecture. Many other questions are there concerning primes which are still unsolved, but some progress has been made in some of these cases. Okay, so after that, congruences. Okay, congruences meaning like we would concern ourselves about like the remainder when we divide. Okay, so to speak, roughly speaking. And yeah, we'll see actually as we go along. And the Chinese remainder theorem, which tells us to find numbers which leave some desirable remainder. Suppose we want to divide by some 36 and leave remainder of 5, and then divide by something co-prime to 36, let's say 35, and say leaves remainder 8. Then this kind of sign.
Sir, you're muted again.
Telling me. Okay. Then what do we have? Okay, then arithmetic functions, Mobius inversion formula, very useful. And arithmetic functions, they are basically functions from natural numbers to any other set. Okay, so these are arithmetic functions. And then we'll have this Fermat's little theorem and Euler's theorem, which has a lot of application. For example, Euler's theorem is useful in building this RSA crypto system. Okay, that cryptography we'll talk about, how we code encrypt messages and how we do the decryption, etc. And primitive roots. Okay, So primitive roots, anyway, we'll see all those topics. These are like kind of generators of some cyclic groups, modulos, primes, etc. Okay, so this thing, we'll see distribution of primes. Okay, this will be the final topic because there's a lot to say about distribution of primes. But depending on the time factor, we'll see what we can do there. And these are the textbooks. This is Barton's elementary number theory book. This is very well. I think this will be good enough for us. Okay, it has it has all the contents that we need and much more. And it is a very readable book. And of course, there are some other texts like Niven, Zuckerman, and Montgomery, an introduction to the numbers. And this Jones and Jones, very nicely written book. It doesn't have exercises, but although it has examples, but this is very nicely written. It's kind of exposition. So this is also a nicely written book. And Rosen, elementary number theory and its applications. There are several other books. As I go along, maybe I will, but these will be sufficient actually for our purpose. Okay. Okay, that is the number theory part. Okay, then we have the algebra part. So algebra, as I said, we'll start with group theory. Okay, which is basically, you can say, so to speak, that the integers under addition, that structure we generalize. But that's integers under addition is a very special type of group, like infinite cyclic group. But we will, because addition is commutative. So it's like an abelian group, what is called an abelian group. So we may drop the assumption, the requirement that our operation is commutative. And we may drop that it is generated by one element, because Z, in some sense, you can get by adding one. Okay, you keep adding one, you get all the positive integers. And you take the additive inverse, and then you get all negative integers by adding -1 sufficiently many times. So that means basically, essentially, it is generated by one element. So it's a very simple kind of group, that is cyclic group. And why it is infinite? Because you don't come back to zero. You don't come back to identity element if you keep adding one to itself. So it's like you get infinitely many elements. So although we generalize the structure of rings under addition, but we will not impose such conditions that commutative or it is generated by one element, because that will be too limited. Okay, so that's why to have more natural examples, we go to permutation groups like maps, bijective maps from any set to itself. That certainly will have an inverse as maps. Okay, so there will be a natural candidate to be a group, and then that will give us enough examples and non-commutative examples of groups. And in fact, later on, Kelly's theorem will tell us that these groups are sufficient because any group can be embedded inside these permutation groups. Okay, so Kelly's theorem is effectively every group is a subgroup of some permutation group. So permutation groups are the ones to be studied. And there are certain basic notions like when we studied vector space, we look at subspace. Okay, similarly, when we have groups, we need to look at subgroups. Okay, as I mentioned here, and there is some relation between order of a subgroup and order of a group, that is Lagrange's theorem. Then there are some special type of subgroups with which you can get a quotient. Okay, we'll see quotient meaning one group divided by the normal subgroup. Okay, so it reduces the size of the group and can reveal some more properties of the original group that we started with. Okay. So these are the topics from group theory. Then rings. Rings are sets with two operations which are compatible, just like integers under addition and multiplication. Similarly, any set with these two binary operations which are compatible. Compatible means distributivity. You perform one first and then you perform the other, or keep in mind distributive. A into B plus C is A into B plus A into C. But in general ring, you have to impose it both ways because multiplication need not be commutative. So you have to separately state that B plus C into A is B into A plus C into A. So left distributive and right distributive, both the properties. And then there will be some special type of rings called integral domains like Z, because when you multiply two integers, you never get zero unless one of them is zero. That's like an integral domain. Ideals. Okay, so ideals are like the analogs of normal subgroups with which you can get a quotient structure. And there are some special type of ideals like prime ideals and maximal ideals. And then homomorphisms. Okay, what does it mean? It means basically structure preserving map. Like when we have two vector spaces, the structure preserving map is a linear map. Like you add vectors and map, or map vectors and add. It is the same thing. But vectors have another operation like the scalar multiplication. That whether you do scalar multiplication first and then map, or map first and then scalar multiply in the other space, they are same. So analogous thing here is ring homomorphism, that whether you perform the operation first and map, or you go to the other ring from R to S. Suppose there are two rings, so this is a map from R to S. Whether you add in R and then map, or you go to S first and then map as elements of S, they should be same. Similar for multiplication. Those are ring homomorphisms. Okay. And field of quotients. Okay. So it's like Z and Q, because Z is contained in the set of rational numbers, which is Q, and rational numbers is the smallest field containing Z. So it's like Q is the field of quotients of Z. Similarly, this can be done for any integral domain, because Z is an integral domain. Integral domain means no zero divisors. Multiply two non-zero integers, you will get non-zero integer. Okay. Then polynomial rings, a very special type of ring. Like you can say polynomials with coefficients from, let's say, integer coefficients. That's an example of a polynomial ring, because you can also add polynomials. If you can add polynomials, you can, if you can add coefficients, then you can add polynomials. Like x square plus 2x, you can add with x cube minus 3x, because you can add the coefficients. So if you take your coefficients from a commutative ring, you have a nice definition of addition and multiplication of polynomials. So we get polynomial rings. And then you can factorize in Z. Can you factorize in polynomial rings? In Z, of course, you can factorize into prime numbers. So similarly, can you factorize in polynomial rings? You will see that yes, you can do, provided you are taking your coefficients from a field, like rational numbers. So, but that brings us back to fields. Although the way our curriculum goes, you did vector space, and what a vector space, they required scalar multiplication by elements of a field. So in fact, already field is something that actually one needs to know before vector space. But anyway, since you are all familiar with rational numbers or real numbers, so we could do 101 that way. That most of the time we consider vector spaces over R. And the set of real numbers, you know, it's a field. What is it? Why it's a field? It has addition, multiplication, and every non-zero element has an inverse. Apart from being commutative, multiplication is commutative, but also every non-zero element has an inverse. Just like every non-zero rational number has an inverse. So similarly, so that's a generalization of Q, so to speak. Okay, the water fields, you can say that is generalization of Q. Okay, the rational numbers, because every non-zero element has an inverse. Then we have something called characteristic, that if you keep adding one to itself, the question is whether you get zero or you go on infinitely. For example, in Q, you have 1 and you keep adding, you never come back to 0. But if you take field of two elements, let's say 0 and 1, that's also a field. Okay, and then you add, then you go back, come back to 0. So it's like finite characteristic, which is important. Then field extensions, because we just don't want to consider the only rational numbers or real numbers or complex numbers, because from rational numbers to real numbers is a big jump. It's an infinite dimensional vector space. R is an infinite dimensional vector space over Q. Okay, Q is countable, R is uncountable. In fact, there will not be a countable basis also. So that way, we need to consider many other fields will come in between, and those intermediate fields will be there. So we want to consider in general field extensions. Like so let's say rational numbers we have, we want something bigger. Field which is, let's say, 2-dimensional over Q or 5-dimensional over Q. And how will I get those? By adjoining roots of polynomials with coefficients from rational numbers. So that's just to give you an overview. Okay, and splitting fields. Okay, that means you have to start with a polynomial. if all the roots are available in a bigger field, then it's called splitting field. For example, you know that in complex numbers, every polynomial has all the roots, but it is too. But often you will need a very small field, like x square minus 2. It's a polynomial with rational coefficients. All the roots will be available in a field containing rational numbers and root 2, like that. So this is splitting field. And finally, finite fields, because for example, cryptography or many other, applications, this is what we'll need. Typical example will be like say Z mod 5Z, all the integers modulo 5. Anyway, we'll be discussing congruences first. Okay, anyway, so this is just an overview. And the book, ideal book for this part is Galilean. Particularly for group theory, it is very suitable. I would say that for ring theory, there are other books which are quite useful. Okay, Herstein's is also a good book, Frelly, and in fact, Damit and Foot, although it may be, you may find it slightly advanced, but it's ring theory and field theory. They are very nicely given with lots of problems, etc. Okay, so anyway, Galilean will be sufficient to start with. Okay, so now what we will do? We will basically start with the number theory, and maybe content-wise, well, this is not. Probably we'll be spending more time on groups and rings, okay, and followed by number theory, and then probably fields. That's what probably it's going to be like. And so what we will do for, okay, so let me see. Okay. Okay, so, and how we'll evaluate the course? Okay, again, this is like a work in progress. So we'll see as we go along, but of course, we cannot just wait like that. So we'll have to rely more on continuous evaluation. Okay, but there'll be some NSEM in some form, and Institute is working on that. What will be the best way to take it? And but we have time. So, but weightage wise, probably it will be like 20 to 25% in the NSEM. So other 75 to 80% will be based on the assignments and some tests that will need to take perhaps every 2 weeks. Okay, because that would be probably because we cannot rely on the semester to start in. Maybe by November things may improve, but it may not. So you will have to rely on continuous evaluation. So we'll go like that. And what I'll do, maybe I'll prepare some slides. I've already prepared, so today I'll do a little bit, and it will be clear to you how we intend to proceed. So I'll make some slides which I will discuss during the class, and later on I'll upload these slides in this team. Okay, so I will upload these slides, and then from time to time I'll upload some assignments, etc. And of course, there are also ways to conduct tests over MS Team itself. But then, as I said, I'll spell out more details as we go along. Okay, so that's what. And okay, these classes, we'll try to get it recorded, and we'll see how big the size is, and depending on that, whether it can be uploaded and all, that also has to be seen. But certainly, the lecture notes in PDF format, I will upload. Okay. Yeah, it is somewhat. I feel unnatural. Like it's like talking to myself. Particularly because when I share the slides, I cannot even see myself, not just you. But yeah, so that's the way we have to proceed. But yeah, do stop me or let me know, particularly if I am inaudible or if the slides are not visible, because I do not know that. So you.
Okay, sir.
Yeah. So now let me share. Let me share this screen, I think. Wait. Okay, wait. Just a moment. Is something showing?
Yeah, it's visible, sir.
Okay. Fine.
Yes, sir, it's visible. Something is visible.
is this the PDF?
And now it's okay, sir.
It is handwritten PDF, right?
Yeah.
Okay, fine. Okay, so as I said, let's just begin with at least some of the things that after my long monologue, let's see, like some topic. Okay, so first one. Okay, this is the notation that this n is the set of all natural numbers 1, 2, 3. Okay, so this is the set of natural numbers. For some reason, n is not visible here. And integers, okay, so as I said, you include 0, then plus minus 1, plus minus 2, the set of integers. So we'll follow this notation. And Q will denote the set of rational numbers, but I will not need this in the first class itself. Okay, so the first thing to start with, okay, so I cannot enlarge it further, I suppose. Okay, the well ordering principle. Let me just see whether I can increase it a bit. No, I cannot do that. Okay, fine. Okay, so what is well ordering principle? That it says every non-empty set of non-negative integers contains a least element. Okay, so what are the requirements? It should be a non-empty set. It should consist of non-negative integers, and then it will have a least element. Okay, in other words, let's take S to be a subset of, I said non-negative, so with 0 I can also include, I mean with natural numbers I can also include 0. Okay, so this is a subset and it should be non-empty. So it should be non-empty subset. Then there will be some element in S such that it is smaller than all other elements in S. So this is the well ordering principle, and that is the starting point for us. So with this we'll be able to prove several other consequences. And one thing to be noted, certainly we cannot make it any integers. Certainly if I take -1, -2, -3, that's a non-empty set, certainly it will not have a least element. So we need this non-negativity. And of course, if I have non-empty, I mean, with an empty set, there's hardly anything to be said, and it will not contain any element, so it will not contain any least element also. So this is the well ordering principle. So what is the Archimedean property? So Archimedean property is that if A and B are positive integers, then there will be a positive integer n such that nb is bigger than equal to A. In other words, n is bigger than A by B. That also you can say that there will be some integer n which is bigger than or equal to A by B. In other words, you can also put it in this language, the set of natural number is not bounded above in some, that way also it can be put later on. But yeah, so this is the statement that we are following from Barton. Okay, this is the statement, I mean, for us, that A and B are positive integers, then there exists a positive integer n which will be bigger than A by B, or in other words, nb will be bigger than A. So let's see how we can prove it using well ordering principle. Okay. Suppose this property does not hold, so we'll prove it by contradiction. Okay, so it will be very effective. So if the contradiction, as you know, is quite useful. So in this case also, assume that this Archimedean property does not hold. What will it mean? That means there will be some A and some B such that NB will always be less than equal to A. Okay, or NB will be strictly less than A, because here I have bigger than equal to. So if I negate the statement, there will be some A and B positive integers such that NB is strictly less than A. So NB is strictly less than A, or in other words, N is basically being bounded above by A by B. Okay, so NB is strictly less than A. So to apply well ordering principle, I will consider a set consisting of A minus NB as n runs over all natural numbers. Because if the Archimedean property fails, then A minus NB will be a non-empty set of positive integers. Okay, so if the Archimedean property does not hold, there will be some A and B in natural numbers such that A minus NB is positive for every N. Okay. That is the failure of the Archimedean properties implication. Then we'll consider this to be our set S, which is A minus NB, and N belonging to N as N runs over N. So it's like A minus B, A minus 2B, A minus 3B, like that. Okay. And since our A we assume to be always bigger than NB, so this is a positive set. And it's non-empty because it has so many elements, it is non-empty. So it should have a least element. Okay, so let's say this least element is A minus N naught B, because all the elements are of the form A minus NB. So there will be something N naught for which it is the least element. Then what is the most natural thing to do is just subtract one more B. In other words, take A minus N naught plus 1B. And clearly it is strictly less than A minus N naught B. But since N naught plus 1 is also a natural number, this also belongs to S. So in S, we found an element which is less than the least element. That's a contradiction. It contradicts the minimality of this element because I'm producing something which is smaller in the same set of positive integers. Okay, so it is a contradiction. Okay, so that means why this contradiction happened? Because we assumed something wrong about this set. Okay, what is that wrong thing? The wrong thing is that certainly it's a non-empty set. So the wrong is that it's not always positive. It has negative. Okay, so that's how we can say that Archimedean property holds as a consequence of well-ordering principle. Okay. Now let's prove another principle that all you must have used in your school days itself. But nevertheless, let's see what is the underlying justification for that. The principle of mathematical induction. What does it say? Formally, if we state it, what does it say? Let S be a set of positive integers satisfying two properties. What are the two properties? First is that 1 belongs to S. Secondly, if K belongs to S, then its successor also belongs to S. That means if K belongs to S, then K plus 1 belongs to S. Okay, so that means if 1 belongs, so 2 belongs, then 3 belongs. So basically, essentially, S should be all of natural numbers. So that still it requires a proof. It requires a rigorous proof, although it is apparent that 1 belongs to S, so 2 belongs to S, so 3 belongs to S. But you should be able to say that, to prove that actually you are not missing out anything, you need to show that the complement is empty. Okay, what is essentially in set theoretic terms, what you have to do, you have to show that N minus S, okay, it is all the natural numbers which are not in S. I'm sure you are familiar with this terminology. In any case, I have stated it here, although I need to improve on my handwriting. Particularly it is like on this tablet PC. Okay, it is worse than my normal handwriting. But anyway, so I try to improve upon that. Okay, so this is the complement of S. Okay. Now certainly it is positive because all the elements of T are positive integers because they are subset of natural numbers. So if it is not empty, then I can apply well-ordering principle. So we'll show that it is empty. But if not, then by well-ordering principle, it will have a least element and we'll work with that. Okay. So suppose S is not N, then T would be non-empty. And we'll show that this will lead to a contradiction. T is non-empty set of positive integers, then it has a least element, which is A. Okay. And since we know that this A cannot be 1 because 1 is already in S, so A is bigger than 1. Why do I need this fact? Because then I can consider A, what happens to A minus 1. Then A minus 1 is still a natural number. Okay, for some reason this belongs to sign did not come here. Anyway, this means A minus 1 is still a positive natural number. And since A is the least element of T, A minus 1 being less than A, strictly less than A, it must belong to S. So A minus 1 cannot belong to T because A is the least element. So it belongs to the complement because it's a natural number. If it does not belong to a set, it must belong to its complement. And you know that if complement of S is T, complement of T is S. So A minus 1 belongs to S. But now let's invoke the second property of the set S, that if K belongs, then K plus 1 also belongs there. So if A minus 1 belongs to S, then if I add 1, that will also belong to S. That means this element A belongs to S as well as its complement. And certainly that's a contradiction because A, being the least element of T, is a member of T, but at the same time, it's a member of S also because it is successor of an element of S. It is successor of an element which is not in T, so that means it is in S. Okay, so that shows that T has to be empty. Okay. Okay, so let me demonstrate this how we actually use induction to prove mathematical statements, and I'm very sure that you all know it very well. But nevertheless, I have to do my job, so I'll have to give an example. So let's use mathematical induction to show that this 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial is n plus 1 factorial minus 1. Okay. So in other words, if we want to see it in the language of the mathematical induction principle that we just wrote, it would mean we need to show that 1 belongs to the set S which satisfies this condition. Let S be the set of natural numbers which satisfies this property. Then we'll need to show that 1 belongs to S, and we need to show that if K belongs to S, K plus 1 also belongs to S. But anyway, we'll not do that elaborately. We'll just say, let this, suppose we check whether this statement holds for n equal to 1, and then check that if it holds for K, it holds for K plus 1. That will mean that 1 is there in the set for a set of integers for which this holds, and so that will be the full set of integers. Okay, so this is here, you all know it very well. So we'll just show that this holds for 1, which is clear because 1 times 1 factorial is certainly 2 factorial minus 1. So it is true for 1. And suppose it is true for K. So suppose if I end up here with K, is K plus 1 factorial minus 1. Then I need to look at the statement, what happens when n is K plus 1. So it's like if I end with K plus 1 times K plus 1 factorial, let's see what happens. Okay, and it's quite clear that this is the additional term. Up till this, we can get it like this by induction principle. So this is the induction principle up to this point. Then I'm adding this extra term. And these arguments are like quite familiar to you all. And we are just seeing that we are getting K plus 2i factorial minus 1. So if we end up with K plus 1, I end up with K plus 1 plus 1. So this is fine. So that's how we apply the principle of mathematical induction. And this is something that you all are familiar with. But anyway, we gave some justification through our well ordering principle, which implied this mathematical induction. Okay, that's the starting point for this course. So yeah, I do not have much today because it's the first class and that's just an initiation. So what we'll do next, we'll move on to division algorithm, which is of fundamental importance. Okay, so anyway, so this is what well ordering principle. But next is what is division algorithm. Division algorithm is quite useful. Okay, so let me just talk for 5 more minutes. Just wait. Okay, so I need to share something else. So let me figure out. Okay. Okay, anyway, suppose division algorithm slide is coming, right? I mean, this course content. Is it visible?
Yeah, sir. Visual, sir.
Okay, anyway, so now, not that I'm going to prove anything or discuss in detail, but just to let you know that what we did today is like cover this first topic, which is like the starting point. And from the next class, from Monday onwards, we'll be starting with the division algorithm. And this is very useful because a lot of subsequent properties will be based on that. And in fact, later on, because being able to divide one element by a non-zero element with some remainder, which is in essence smaller than the divisor, is a very useful property. Certainly we'll prove it for integers. Later on, we'll try to do that for rings also. Okay, and if a ring has that kind of property, that will be known as Euclidean ring, and Euclidean rings are very special. Okay, so this division algorithm, of course, for integers we can directly compare the divisor and the remainder, but in general we may not directly compare, like one polynomial and another polynomial. I cannot directly compare polynomial, but I can compare their degrees. So later on, actually, in fact, maybe you have done some division with polynomials also. Okay, to divide one polynomial by the other and try to get a remainder of smaller degree. So in that sense, when it comes to polynomial, remainder should be smaller in degree. Similarly, they are like general analogs. In some sense, okay, or in some norm, the remainder should be smaller than the divisor. Okay, that is it's a very useful principle, and whenever we have this algorithm, then a lot of things are simpler. Okay, like finding GCD, etc. Okay, so that's what we'll talk about in the next class. So I think if you have any question, you can let me know now, because okay, so yeah, so otherwise I'll stop here and then yeah. Okay, any question? Yeah, okay, so I should unmute, I suppose. Yeah. Saket. Yeah, any question? Okay, so if there is any question, you let me know. I don't know whether I should or if you are willing to say something but you're unable, then also maybe this chat. Okay, this box is there. Okay, I am muted. I see, now I see the messages. Okay, I see. Okay, any question, you let me know. Okay, or you can write on the side this chat option also, that if you have any question, then you sometimes maybe if I don't miss, or so you write on the side. And if you're not having any question, maybe we'll stop now, and from Monday we'll start with division algorithm. Okay, any question? Sir, do we have absolute grading? Well, okay, so these questions, well, I would say that right now I cannot answer immediately, because as I said, that it has to evolve as we go along. Okay, but for the time being, I can say that our NSEM will be like 25% or so, maybe 20 to 25%. Yeah, so recordings, yeah, I'm recording this session. Hopefully I'm getting it the right way, so that I'll be able to get the video, and then we'll see that if the size is sufficient for uploading all these lectures. But certainly I'll upload the slides, and I'll try to upload the videos. I'll try to reduce size with some handbrake or something is there, so we'll try. How can you get course material? Yeah, I'll be uploading it in MS Team itself. I think there's like class materials option, so I'll upload there. And hopefully these videos also will find a place to be uploaded. Okay, so yeah, so I'll inform you. Any other queries?
Sir, I guess when you stop recording, the recording will be there in the chat itself.
Okay, recording will be there in the chat itself, huh?
Most likely.
Okay, fine. Okay, so I'll find out. Now I'll stop recording, huh?
Yes.
Just to see whether what happens